Welcome to bonding part 2. Today we're going to discuss about bonding part 2, and I will share with you the learning objective first. So let me open up the lecture slide. Right, so for chemical bonding part 2, there are 3 important subtopics. The first one is valence shell electron shell repulsion, known as VSEPR or VSEPR, and theory of covalent bonding, which consists of valence bond theory, in short VBT, and molecular orbital theory, in short MOT. So in this topic, bonding part 2, the learning objective is to describe 5 basic molecular geometry. Okay, we have learned about 2D structure by using Lewis structure, that is 2D. So molecular geometry is a 3D form of the compound. Explain the basis of VSEPR, and you apply this theory in predicting the molecular structure. And the third one, of course, is the VBT and the MOT concept theory in explaining the covalent bond. So let us discuss the VSEPR first. So molecules or compound containing 3 or more atoms will have many different shapes. And this is the 3D form. We have discussed the Lewis structure in 2D form. So how do we determine the shapes or the molecular structure of this compound? So first, we discussed about VSEPR. So the most important thing that you have to understand about VSEPR is how it works. This is a tool to be used to identify the molecular structure. And before we can use that VSEPR to identify the molecular structure, there are a few terms that you have to understand. First, the term of electron domain. So in any compound or molecule, electrons will be in either bonding domain, means that electron that is inside the bond, okay, or electron that is in non-bonding domain, means that electron involved in lone pair. So all electrons in a single, double, or triple bond are considered to be in the same bonding domain. So it is considered, if you have a double bond, triple bond, it is considered one bonding domain. So let us watch a bit on a YouTube video explaining the principle of VSEPR.
Because this will affect how the molecule does chemistry. A model space, because this will affect how the molecule does chemistry. A model we can use to analyze molecular geometry is called the VSEPR model, which stands for valence shell electron pair repulsion.
Very long.
This is how we will predict the shape of a molecule. Atoms are surrounded by clouds of negatively charged electrons. And when you have atoms in a molecule together, these electron clouds repel each other. Because of this, a molecule will automatically adopt.
Okay, remember that the electron repels each other.
A particular geometry so as to allow all the atoms to be as far away from each other as possible. Think of these electron clouds as magnets of like charge.
So when the atoms in molecule or compounds arrange themselves so that it is as far away as possible from each other, that is the basis of VSEPR, where electron is also arranged as far as each other to reduce the potential energy. That is the basis of VSEPR.
The closer you put them together, the more potential energy they have. Things want to be at the lowest energy possible.
Yeah,
so
the
if you let
lowest
go,
energy
they will push
possible.
apart, lowering their energies. Atoms will do the same thing. Take carbon dioxide, for example. The carbon atom has 2 electron domains, or areas of electron density extending from it. In order to participate in these bonds, the carbon takes an s orbital and a p orbital and hybridizes them.
Right. Let's stop there for this YouTube video. We move back to the slides. Remember about the bonding domain and non-bonding domain. So that is very important for you to understand before we can move on to use VSEPR to determine the molecular structure. So we have watched the video just now. If you remember, the basis is the electron or the atoms are arranged so that it is as far away as possible from one another. This is to reduce the potential energy so that the compound or the molecule is stable. Okay. So now let's move on to the definition of electron domain. So we have to learn about the general electron domain. And from there, we will need to split that general electron domain to bonding domain and non-bonding domain. So this is the table that you have to memorize. Let's say the compound has electron domain. Remember the word electron domain 2, then the electronic structure, not molecular structure, the electronic structure is linear. Let's say the number of domain, electron domain is 3, then the electronic structure is planar, triangular, and so on. So you have to study this table. So when the question usually asked is if you're given a certain, for example, compound, you have to identify the electronic structure and the molecular structure, which is different because electronic structure based on total number of domain, but when we are discussing molecular structure, it has to be separated to non-bonding and bonding domain. So let's use this VSEPR. So how to use this VSEPR? VSEPR can be used first by drawing a basic Lewis structure. Okay, so you cannot avoid by incorporating the first topic or the bonding part 1, which we have discussed on how to draw the Lewis structure. So first you draw the Lewis structure and count the number of electron pairs surrounding central atom, identify lone pairs and bonding pairs, and you can determine the basic geometrical shape, which is the electronic structure, the one that I have shown just now. Okay. So this is also known as basic geometrical shape, right? So these are basic geometrical shape based on total number of domain, okay? So after that is from the geometrical shape, you can identify the specific molecular structure, geometrical shape of the molecule, which is the molecular structure. So from here, you have, for example, 4. If you have electron domain of 4, okay? So the general structure or the electronic structure is tetrahedral. But if you move on to split into, out of 4, let's say 0 lone pair or 0 non-bonding, then the structure will be the same, tetrahedral. But if you have out of 4, 3 electron involved in bonding domain and 1 electron involved in non-bonding domain, then you have what we call as trigonal pyramidal. You can see here 3 pairs of electron involved in bonding and 1 pair of electron involved in non-bonding domain. The basic structure is tetrahedral, but the actual molecular structure you can see from here is trigonal pyramidal. So let's say out of 4, you have 2 involved in bonding domain, 2 pairs of electron, and 2 pairs of electron involved in non-bonding domain. You can see now out of general structure, the final structure is band, V-shape or non-linear. Now, if you look at other examples, if you have 5 bonding domain, 5 domain of electron, and if you have 0 non-bonding, then you have the same general structure, which is trigonal bipyramidal, right? And if you split it into 4 and 1, you have distorted tetrahedral, 3, 2, T-shape, and so on. So these tables you have to remember, and you have to able to draw this, all this structure for you to able to answer exam questions. So now this, you have 6, and 6 you can split to 5, 1, 4, 2, and so on. So we're not going to discuss all these. You have to look at the slides and try to relate the first table, which is the general domain. Out of this general electron domains, you split into non-bonding and bonding domains, and what is the actual molecular structure. Well, in part 1, bonding part 1, remember that we talk about dipole moment. When dipole moment is not 0, means that you have polar molecules. Okay, so the higher the dipole moment value means the more polar the molecules are. All right, so in order to identify the polarity of the molecule or the compound, we can use this molecular structure to identify based on the symmetric of the compound or the molecules. So you can see from here, CO2 is non-polar, okay, because the dipole cancel each other, okay. So if you derive from the general electronic structure, okay, electronic domain to molecular structure, okay, can come out that the CO2 molecules is linear, okay. Okay, same goes to BCl3 and CCl4, because if they are viewed in 3D structure, okay, all the dipole moments are cancelled each other, okay. So let's say if you have asymmetric molecules or compound, you have here chlorine attached to carbon, and here hydrogen. You can see chlorine is highly electronegative, and carbon is has higher electronegativity compared to hydrogen. So you can see it is not cancelling each other, and therefore it has a dipole moment, and the molecule is polar. Okay, so from there, okay, we can conclude that VSEPR, okay, the principle of VSEPR is to arrange, the atoms are arranged as far as possible from each other to reduce the potential energy, okay, and the VSEPR is used first by constructing a Lewis structure, okay, and then by identifying the electronic domain, okay, of the electrons, and from there you can identify the general structure based on the first table, And second one, out of the general structure, out of the general domain, electron domain, you split the domain into non-bonding and bonding domain. And from there, you can identify the molecular structure, the actual molecular structure.